Hello, my name is Michael Heisel. Today I will be talking about eddies in stably stratified boundary layers. My colleagues on this work are Marcelo Chemecki, my postdoc advisor at UCLA, Peter Sullivan at NCAR, and Gabby Catul at Duke University. I'd like to start off by discussing the presence of attached eddies in neutrally stratified canonical wall-bounded flows. From the attached eddy hypothesis of Townsend in his textbook, we have that the logarithmic region is populated by a superposition of eddies that extend down to the wall. This superposition of eddies leads to coherent features in the flow whose size is proportional to distance from the wall, which I'll be using the z-coordinate system for this. And these features have a characteristic velocity proportional to the shear velocity u tau. You can see this behavior in a number of different features depending on how you conduct your analysis. For instance, this has been seen a lot in recent years in the behavior of momentum streaks, low and high speed momentum streaks that are often associated with packets of hairpin-like vortices. You can also see this distance from the wall scaling in streamwise rollers or the weakly rotating structures that are associated with the momentum streaks. You can also identify it from resolvent analysis in the hierarchy of attached eddies, or you can see it in the more general classification of uniform momentum zones, which is the framework that I'll be using here today. There is a correspondence between these attached eddies and the mean flow profile, both in terms of the attached eddy hypothesis and in experimental observations, where the instantaneous features have a scaling behavior with u tau and distance from the wall z that matches the scaling behavior of the mean velocity gradient shown here on the right-hand side. This provides us a means to link the instantaneous features in the flow to the overall mean through considering an ensemble of all of the instantaneous events. The question for our work today is what happens to these instantaneous events when the flow becomes stratified, and how can we relate changes in the eddy behavior to changes in the mean flow profile when you start to introduce thermal stratification. Stably stratified flows are common in nature, specifically and most notably during the nighttime in the planetary boundary layer. You also see it in polar regions, particularly in the wintertime, in fluvial open channels in hot and dry climates, and then also along the bottom of the ocean. To look at stably stratified flows, we used existing large eddy simulations that are wall modeled and conducted on a 1024 cubed grid, making them relatively high resolution. These were conducted by our co-author Peter Sullivan and presented in Journal of Atmospheric Sciences in 2016, where an example temperature field is shown here in the upper right plot. The simulations included 5 cases ranging from neutrally stratified to very stably stratified, and in order to mimic a planetary boundary layer, the simulations include a Coriolis force and a stable capping inversion, which you'll see in just a moment. Shown here are mean flow profiles for the different stability cases. On the left is the potential temperature theta in units of Kelvin, and on the right is the horizontal wind speed. In the temperature profile, you can see the stable capping inversion that I mentioned on the previous slide. The start of this capping inversion is considered to be the top of the boundary layer here, and I'm giving it the notation Zi, which is traditional in atmospheric science. The different stabilities are imposed by using a fixed surface cooling rate that increases as you increase the stability, which you can see where you have a flat profile in the temperature for the neutral case, and then you have an increasingly cooler surface as you increase the stratification. The temperature profile is initialized using a geostrophic wind forcing that's equal to 8 meters per second, as you can see in the right-hand plot. And our stratification is characterized in terms of Zi over L, where L is the Obukhov length. The critical scaling parameters are u tau, the friction velocity, theta star, which is associated with the surface heat flux and u tau, and then the Obukhov length that I previously mentioned. What we'll be focusing on today is the behavior of these mean flow profiles, specifically in the lowest portion of the boundary layer corresponding to the logarithmic region or the atmospheric surface layer. Shown here are gradients of these mean flow profiles in the bottommost portion of the boundary layer, and the gradients are shown relative to the log law scaling, where you can have a log law in the temperature with theta star over kappa z, and then equivalently in the velocity using u tau over kappa z. You can see that only the neutral case, this black line, is close to 1 throughout the surface layer, indicating that it has an adherence to the log law velocity profile. However, as you increase the stratification and increase your distance away from the surface, you increase your departure away from the log law. So our question moving forward is what's happening to the coherent features in the flow that correspond to this increasing departure from the log law in the velocity gradient and the temperature gradient. To study this, we used the existing framework of uniform momentum zones that I introduced earlier in the presentation. On the left-hand side, we have an instantaneous velocity field focusing on the bottommost portion of the boundary layer, where you can see that this field is fairly well approximated as a series of uniform zones. The middle panel here shows this approximation where we're assuming the velocity is constant inside each of the zones. If we compare an instantaneous profile that you get just taking a slice from the middle of these fields, it reveals a stair-step-like shape in the instantaneous profile that can be characterized in terms of the difference in velocity between adjacent zones, delta U, and the vertical thickness of the zones, H. And what we'd like to do is see how these properties correspond to the mean gradient that you get as a result of ensemble averaging each of these instantaneous events. We applied the same methodology to detect uniform temperature zones where the instantaneous turbulent temperature field is shown on the left, and we approximated each of the well-mixed zones using a constant temperature, and that yields this stair-step shaped temperature profile that can be described in terms of the apparent jump in temperature delta theta and the vertical thickness h, which we can relate in the same way as the velocity to the mean temperature profile that you get on the right hand side. In each of these past two slides, I've used the most stable case as an example, indicating that this presence of uniform zones for a neutral boundary layer is similarly present for a stratified boundary layer. In this slide, we have average properties of this jump in the velocity and temperature, and the averages are conducted in binned intervals of distance from the surface such that we get a profile within the surface layer or the logarithmic region. These profiles are shown dimensionally for the velocity on the left and the temperature on the right, just to show the variety of values that we get. And then if you introduce the surface scaling parameters, the friction velocity u tau and the theta star for the temperature, you get a good agreement across all of the data sets. Shown here are vertical profiles for the uniform zone size in terms of their vertical thickness. On the left is the momentum zones. For the neutral case with the black squares, the zone size increases as you move away from the surface. This is consistent with attached eddies whose size is proportional to distance from the wall. However, as you introduce stable stratification, the wall normal distance scaling is quickly lost in the sizes of these momentum zones, and by the time you reach the very stable case, these yellow data markers, the zone size is relatively independent of distance from the surface. The same behavior is observed for the uniform temperature zones on the right. The only difference here is that we don't have the neutral case because there is no organized temperature field in that simulation. This has significant implications for the mean flow profiles. In the neutral case, we have scaling behavior in the instantaneous features that can be linked to the overall mean velocity gradient that yields a scaling behavior on both u tau and distance from the surface. As you introduce stable stratification, there is a reduction in the zone size that leads to more steps in these stair-step shaped profiles that corresponds to a steepening in the overall mean velocity gradient. As you become very stable, the reduction in zone size eventually loses the dependence on the wall normal distance entirely and becomes z-less, which is the terminology used in the atmospheric sciences community. Finally, I'd like to briefly discuss implications for mixing using conditional profiles relative to the edges of detected temperature zones, as illustrated in the upper right cartoon, where we have a cool temperature zone underneath a warmer one. As we've seen in a number of the previous slides, you have a temperature that's relatively uniform within the zones, and then a bulk of the difference is associated with these thin gradient layers. The implication for mixing is that as you increase the stratification, the suppression of mixing is not necessarily going to increase equally throughout the entire flow volume. It's going to be highly localized and concentrated along these thin gradient layers that separate the relatively well-mixed zones. To briefly summarize what we've seen, the organization of quasi-uniform zones and thin shear layers that you see in a neutrally stratified boundary layer are also present under stable stratification, both for the velocity and the turbulent temperature fields. The thin gradient layers and the differences in velocity and temperature across these layers maintains a scaling relationship with U tau and theta star regardless of stratification. However, the sizes of these uniform zones decreases with increasing stability, and they quickly lose their dependence on distance from the surface C, such that the main eddies associated with the mean flow profiles become detached from the surface, which you can see in the illustration here at the bottom. Finally, I'd like to acknowledge funding support from National Science Foundation and note that results from this presentation are currently under revision but are posted on arXiv in a preprint. Thank you.